Okay, so chapter 21 is about a process called the Gram-Schmidt process. And what that process is for is it's for taking as a starting point a basis, B, for some subspace W of Rn, and turning it into an orthogonal basis, which means converting it so that all of it, modifying all the vectors slightly so that they're all orthogonal to each other. And that's what remember, that's what it means to be an orthogonal basis. And let's just start by going through that again. So if you have a basis B for subspace W of Rn, well, a basis is orthogonal if each of the vectors is orthogonal to each of the other vectors, right? So xj is orthogonal to xk. And that's got to be true whenever j and k are not the same. Right? That's what it means for all. That's how you can express this mathematically, that all those vectors have to be orthogonal to all of the other vectors. Now, what does it mean to be an orthonormal basis? Well, remember, it has to first and foremost be an orthogonal basis. So before even being considered as an orthonormal basis, it had better first and foremost be an orthogonal basis, but it has to satisfy the extra condition that each of the vectors inside of it are of length 1. They're all unit vectors. So the norm of xj is equal to 1, and I'm just going to say that's got to be true for each, not just for some j, but for every value of j that makes sense as an index here, right? So start 1, 2, all the way up to k. And remember what the key feature is? Let's go also just quickly remind ourselves, what's the key feature of an orthogonal basis? Well, if you have an orthogonal basis, B, so now we're going to start with the same assumption, but this time we're going to assume we have an orthogonal basis, B, for a subspace W of Rn. Well, if you start with a vector u in W, so start with any vector at all that is in W, and you can write it in the following way. You can decompose it as the projection of u onto x1 plus the projection of u onto x2. Right? I can project it onto each of the vectors in the orthogonal basis, and then I can add up the results of those projections. And if I do that for x1, x2, all the way up to xk, then I'm actually going to obtain a whole bunch of orthogonal components of the vector u. One of these components is parallel to x1, the other next one's parallel to x2, and so on. That's how these projections work. So if the vectors in B are all mutually orthogonal, then so are all these terms. Right? All these projections are going to be mutually orthogonal as well. So you can break up u into a whole bunch of orthogonal components that way. And if you actually spell out what the projection means, this, by the way, and before I go any further, you can't do this if you don't assume that the basis B is orthogonal. Right? This statement is false if you only assume that B is a basis. If B is just a basis and you don't know anything else, that's not enough to write this down. But if you do know that B is an orthogonal basis, then you can write this down. Okay, but if you do, now let's say you're in that situation. Now, what does the projection formula give you? Well, the projection of u onto x1, well, I just have the dot product of u and x1 divided by the dot product of x1 and x1, and all that gets multiplied onto x1. So that's what the first projection is. The next projection, I have the dot product of u with x2 over x2 dot x2, and that's going to be multiplied by x2. And I do this with each one of the terms, and I'm going to have this last one will be the dot product of u with xk all over the dot product of xk with itself. That's a bit sloppy there. All finally multiplied onto the xk. So that's what you get if you just unwind what all those projections actually mean. Now, and here's the cool part, if your basis happens to be orthonormal, let's say, so if B were orthonormal, that wasn't an assumption, but I just want to add it as a comment. If B were orthonormal, then the dot product of x1 with itself would just be 1. And same with the dot product of x2 with itself. This would be 1 as well. And same with all the way up to the very last vector, because all these vectors will be of length 1. So you would just end up, in that case, it'd be really easy to write down the dot product of u with x1 times x1, the dot product of u with x2 times x2. I'm getting nervous here, hope I'm going to fit it. And I would go keep going until they got to the very last vector in the list, so in the basis, the dot product of u with xk multiplied by xk. Okay, so I barely fit that. That's what you could go that one step further if your basis were an orthonormal basis. So you can start to see why this simplifies things, right? And by the way, what do I mean? What are you actually doing when you calculate these coefficients? If b is a basis, let alone an orthogonal basis, but if b is a basis for a subspace, then any vector u in that subspace can be written as a linear combination of your basis vectors. But that doesn't tell you how to actually get these coefficients, whereas in this setting, now you do have a formula. Just calculating the coefficients required to form your vector as a linear combination of basis vectors is as simple as working out these dot products now. So that's actually very attractive. But remember, if your basis is not orthogonal, then you can't even do this, let alone this. Okay, so that's the purpose. That's why you should care about an orthogonal basis or an orthonormal basis. But now for the Gram-Schmidt process, which answers this question. So let's say you have a basis, B, for a subspace W, but it's not necessarily orthogonal. What do? You apply the Gram-Schmidt process, okay? And here's what it looks like. Okay, you can see I've stated the Gram-Schmidt process very formally here in terms of a formula, but I'll just show you what it looks like first, and then we can go back up and look at the formula in just a moment. So here's an illustration. Let's say you've got four vectors, x1, x2, x3, and x4. You're going to form a new basis with these as the vectors. So the first vector, u1, just take it to be x1. There, you got one vector already. Just take a copy of x1, not going to change it one bit. But then now for u2, what you're going to get is you're going to take x2, but then here's what you're not going to stop here, because if I took x2, my u2 to be x2, then there's no guarantee that u1 and u2 are orthogonal, because there's no guarantee that x1 and x2 are orthogonal. But we can make u1 and u2 orthogonal by subtracting. Okay, here's the thing: there's going to be some component of x2 that's parallel to x1. So it might not be that x2 is parallel to x1, but it's going to have some little piece of it that's parallel to x1. So we're going to take that away from it. We're going to subtract it. We're going to subtract. See, the projection will let us do that. We're going to subtract the projection of x2 onto u1, because that will be the piece of, that's the piece we want to throw away of x2. So you subtract that projection, and now they're orthogonal by design. You could check this using formulas, you could check this by using direct calculation. You're just using properties of projection and vector subtraction and the dot product, the way they interact. You could show that these two vectors are always going to be orthogonal. But what do you do for the next vector? It gets a little bit more complicated each time. But your third vector, u3, you're going to take it to be x3. But there's going to be some, just like before, you got to take into account there could be some bit of x3 that's parallel to x1. So we want to throw it away. So we're going to subtract the projection of x3 onto u1. That gets rid of the bit of x3 that's parallel to u1, so we want to throw it away so that u3 will be orthogonal to, u3 will be orthogonal to u1. But we also need to take into account that there could be a piece of x3 that's parallel to not x2 anymore, but u2. There could be a piece of x3 that's parallel to u2. So we need to throw that part away. So you're also going to subtract another projection. You're going to subtract the projection of x3 onto u2. And then that way, now you've thrown away the piece of x3 that's parallel to u1. So that's why the result is going to be orthogonal to u1. And then here you throw away the portion of x3 that's parallel to u2. That ensures that the result is going to be orthogonal to u2 as well. And you just keep going on this in this fashion. So u4, I'm just going to take it to be x4, but now I have to subtract three projections. I'm going to project x4 onto u1 and then subtract that. I'm going to project it onto u2 and then subtract that. And I'll project it onto u3 and then subtract that. And then that's going to get in my u4. And you see, each time you go further along through the list of vectors, you have an extra projection to subtract each time. And that's why this actually gets very computationally demanding very quickly, even for numbers that seem fairly simple at the start. So yeah, what's this last term? Minus the projection of x4 onto u3 finally. So see, we took u4 to be x4 minus its projection onto all the other vectors we've formed at each point in the list. At each point in the stage, that's what you do. So think about right from the beginning. Take u1 to be equal to x1. There's nothing to subtract because there was no other vectors that we formed before now. But then when you move on to u2, well, you've already constructed u1. So when you take u2 just to be x2, but subtract its projection onto u1. But then when you go to compute u3, well, you've already computed now two vectors, u1 and u2. So when you take u3 to be x3, you have to subtract the projection of x3 onto both of u1 and u2. You see what I mean? You're always projecting onto all the vectors that you've already formed. And if you just go back up to the actual formal statement of the algorithm now, you'll see that's what this summation is right here that's happening. You take each um to be equal to xm, but then you subtract the projection of xm onto all the previous u vectors that you already formed. And that's what's happening inside those square brackets. That sum is just referring to this, this, and this. And by the way, in the case of the first term here, when m is equal to 1, then in that case, this is actually just a completely empty sum. Let's just add this as a remark here. When m equals 1, then you have the sum from j equals 1 to, well, if m equals 1, 1 minus 1 is 0. So you've got the sum from j equals 1 to 0 of the projection of xm onto uj. Okay, well, remember how to interpret these. You start with the first index of j equals 1. Well, that's already greater than your maximum bound of 0. Right? 0 is an upper bound on all the indices. So if your first index, your initial value for the index is already greater than your max value for the index, then you have a sum consisting of 0 terms, or it's a completely empty sum. So, well, then let's take it to be the 0 vector in that case. That's the only sensible way to interpret it, and that's actually what you're supposed to do anyway. So it actually works out perfectly because you're subtracting 0 here. Okay, so that's what it looks like in general. And you can see that, so just to read through the statement formally now, so if you have start with B as a basis for a subspace W, you have no restrictions on it. You're going to form a new basis. You can see it's been called B prime here, so it's a modified version of your original basis B. And you're going to use the vectors U1, U2, all the way up to UK. And each one of those vectors, U1 to U1, U2, all the way up to UK, each of those are going to be converted with calculated using this formula. So that's the Gram-Schmidt process. And that brings you up to the level of an orthogonal basis. If you want it to be an orthonormal basis, well, then that means you additionally want each of the vectors to be of length 1. And in that case, you just replace here. We've already, at this point, we would have used the Gram-Schmidt to get an orthogonal basis, B prime, but they might not all have length 1. So just replace each of them with a unit vector in the same direction. So in general, we'll just replace uj with 1 over the norm of uj times uj, right? Do that with each of the vectors you computed using the Gram-Schmidt process, and then let them take the role of this vector, and then just replace it with 1 over its length. Do that for each of the basis vectors, and now that'll turn an orthogonal basis into an orthonormal basis. So, and actually that leads to this remark here. At any point during the Gram-Schmidt process, you can scale the length of the vectors that you've already computed to any degree. If it helps you in some way, like maybe it'll help you avoid working with fractions or radicals or really messy numbers, then do it, right? Take advantage of that. And so at any point in the process, you can put it this way, you can adjust the length of any of your u's at any point if it seems like it's going to help things. And quite often you might convert them to length 1 right off the bat. That might not always be what you want to do, but that's certainly an option. You could, at each point, right after I set u1 equal to x1, I could say, okay, now actually let it be 1 over the norm of x1 times x1 and scale its length so it's 1 right off the bat. And then I could do the same thing with this vector u2 right after I compute it. Or maybe I don't want to. It's totally up to me, because the way we stated the Gram-Schmidt here will just take you to an orthogonal basis. And it's up to you. If you want to turn it into an orthogonal basis, you can just do this step at the end for each vector. Okay, let's look at an example.